This work is being done in collaboration with the Stanford Linear Accelerator Lab in Palo Alto, California. The lasers aren't working. So these are our, this isn't working at all. You know what, I'll just operate from up here. Yes. Yeah, it worked yesterday. So these are the folks behind my name that are conducting most of the research. I serve as project manager for the government at the National Energy Technology Lab. We work in conjunction with them to fund projects and make sure that they're meeting their objective goals. So the team is mostly from Stanford. The problem here that we're trying to address is unconventional recovery from shale oil and shale gas. And as many of you know, the problem that we have is that our recovery factors are only between 2 and 19% in the shale gas, with an average of 13%. And for shale oil, we're getting less than 2% recovery. Obviously, this isn't good enough, and we need to study it more. So we're going to put this on the chart here. This is a cumulative production curve, and if my pointer was working real well, you can see that there are two lines. One is the black line that talks about current technology. The other line for cumulative production is the green line, and so that gap between the two is really where we can improve our environmental efficiency and improve our economic efficiency. So we'd rather be on the green line than on the black line, basically is what this is showing. We also talk about environmental issues with any government-funded research. And the other factor is, can we sequester the heavy metals and the radioactive compounds in the subsurface? But most of this talk is going to focus on the first big question, which is improving recovery rates. So what we're trying to do in this research is to build a knowledge base. And that knowledge base that we're trying to improve is the chemical and physical evolution of the oil and gas reservoirs. So the more we know, the more we can improve our techniques. And to do that, we need to improve our fracture fluid compositions and improve our STEM processes. So the way the project is set up, it's set up between spectroscopy, imaging, and modeling, numerical modeling. And basically these feed one another. The observations that we see in this spectroscopy and the imaging limit our modeling part of the project. So you can see that up in the upper left, that's the Stanford Linear Accelerator Lab. They actually have a particle beam microscope. It produces light that's probably 6 times that of the sun. And so they can look at rocks in unique ways that very few people in the country can look at them. They can oftentimes see through thin sections. So it's real important to understand that we are using some high-powered equipment in some of this work. We also use very basic information too, like jar tests, geochemistry tests, and looking at the evolution of rocks and water from the system. So this is our conceptual project model. If you look at the left-hand part of the graph, you will see that the scale reduces from millimeters to nanometers, and these are the scales of observation that we're caring about. What you see in blue is water imbibition into the rock matrix and fractures. So what we're seeing is once the water imbibes into the rock, and there's a combination of acids, there's a combination of organics that are coming in with the water, we're creating chemistry. There's radical difference between the chemistry of our stem fluid and the chemistry of our rock. The rock rock matrix frequently is in a reducing environment, this water that comes in is oxygenated. So we are creating chemistry. There is no doubt about it. In our graph here, chart here, we can see that calcium bicarbonate's coming out of solution in the fracturing fluid in the far left-hand side of this diagram. We also, so calcite is, dissolving basically. And the other part, iron is coming out of solution and occluding fracture planes potentially. And at the nanometer scale, at the very smallest scale, we're looking at what's happening to kerogen, clay minerals, and even pyrite in solution. We're going to show you some diagram or some spectroscopy figures from that work. So like we talked about, the very common part of the fracturing process is the inclusion of hydrochloric acid to remove asperities from the well bores and start the frack process. So you're starting immediately to put the system into disequilibrium with the production of oxygen and acid going into the rock mass. So what's happening here? The first thing that is happening when you start reacting the rock mass with this stimulation fluid is you start getting calcite involved in the reaction. So the carbonate minerals are seeing dissolution in the process. And in the lower right, you can see from our SEM diagram or photograph that there are bugs put into the rock matrix as a result of this dissolution. And also, there's a negative side of this too, and that is there's capillary barriers formed from the water added to the rock matrix. We also get silicate mineral dissolution, so aluminum, silicate, and trace metals, heavy metals are coming out. We also have oxidation of pyrite, which is probably happening later in the process than the other two. And then finally, we want to show here that it's important to understand what's in your rock matrix. You can't just call every carbonate-rich rock the same in terms of how it's going to react with frac fluid. The forames that we see in this SEM diagram actually are silicate coated, and so the carbonate is included within those forames. And so that carbonate is not available for reaction. So it's important to understand where the various chemicals are distributed throughout the rock, whether they're armored from forame tests or other things. Okay, so we talked about calcite reactions, we talked about silicate reactions, and finally we talked about pyrite reactions. So we want to look at the rates. We already talked about calcite being faster than the silicate and the pyrite reactions. So we precipitate this material out. Where is that happening? Is it going to impact our fractures? Is it going to impact the matrix? And we also want to see where this precipitate's actually occurring. We call it shale damage, this secondary precipitation that's occurring in the rock. So here we have a diagram showing the various rock chemistries that we've studied. Marcellus is shown in the red, and I'd point that out if I had a pointer, but you can see it there in the left-hand side of the triangle. To the right is carbonate-rich Eagleford, and the way we're conducting this part of the experiment is we're using reactors, chemical reactors, which are 250 milliliters of stem fluid and rock fragments. And we're keeping these for up to 6 months. So we're going to study the rock chemistry and the water chemistry at various points throughout time here. And you're going to see later on in the presentation that there is a difference between the way a Marcellus rock is going to react